All right, well, I think this might be the moment that a lot of you have been waiting for. We are finally, after many weeks of doing linear algebra, and I love linear algebra, but you know, what's better than just linear algebra is doing linear algebra with differential equations. So this is what you've been waiting for. We are going back to differential equations now. We've spent many weeks getting tools of linear algebra together, and we're going to use those tools to do stuff that we could never have done back in January and the beginning of February at the start of the class. So it's one of the beautiful things about the class, as I've been saying all along, is the way it blends the two subjects together. So we are going to get started on differential equations with the knowledge of linear algebra that we've just gained. And we're going to see the linear algebra showing up like all over the place pretty much right away. So this is really cool. This is chapter 8 in our book. So chapter 8 is called Linear Differential Equations. Now, we've looked at linear differential equations back in chapter 1, but when we did that, we were looking only at first order linear differential equations. What we're going to do here is we're going to look at linear differential equations of any order n that we want. Nth order linear differential equations. Okay? Just a couple of pieces of notation that will be useful for us here to get us started. We're going to be sometimes looking at functions that are defined on an interval I. So I is going to represent an interval. This is an interval within the real numbers. It might actually be the whole real numbers, or it could be just an interval inside of that. Then we have a C super 0 of I. This is going to be the set of continuous functions on I. Just think calculus functions if you want. Think about calculus functions. C1 of I, this is the set of one-time differentiable, I'll just abbreviate that as diffable, functions on I. So you can take one derivative of the function. Any such function is in that set. And then so on and so forth. C super k of I is the set of functions that you can differentiate k times. But sometimes you can differentiate a function for a while, but then after a few derivatives, you can't anymore, right? You might end up with fractions, dividing by zero issues, things of that nature. So these are functions that you can differentiate a certain number of times, okay? But really what I want to focus on, and where we're really going with this, is not so much this notation. This is just kind of clutter in the background. I want to go back to the function that we've actually looked at this before when we were studying linear transformations. It's the function that just takes derivatives of the inputs. So I'm going to define d. Normally we would call this t. But because we're going to be taking derivatives so often, we're going to switch the notation now, and I'm going to use a d, a capital D, for the derivative operation, or the derivative transformation, if you want to think of it that way. Okay? So if we're going to take a derivative, we have to have a function that we can at least take one derivative of. And the result of taking a derivative of something is going to be a function that is continuous. Okay? Okay, so I've already kind of let the cat out of the bag here. D of any function f is just going to be f prime. So every time you see d, it just means take derivative. Okay? If I see multiple powers of d, so like d to the k of f, well, that's going to be only applicable to a function that you can differentiate k times, but this is going to be the kth derivative of f. Okay? It's just really d of d of d of d of f, right? You're just differentiating again and again and again, like that. Okay? So what I want to do is go back and look at what the form of a linear differential equation of order n would look like When I say go back to it, we did it the first week of the semester. Okay, might have even been the very first lecture. It was way, way early on. I want to write that function down again, and then I'm going to rewrite it using my D notation, this new D notation that we have introduced right here. Okay. By the way, recall that D is linear. This class would not even exist if D was not linear. We could not imagine combining linear algebra with differential equations if taking derivatives was not a linear operation. But yes, derivatives respect addition. The derivative of f plus g is the same as the derivative of f plus the derivative of g. And the derivative of a constant times f is just that constant times the derivative of f. Right. So that is the setup. That's the background. So let me just recall for you. Let me just recall an nth order linear differential equation, right, has the form. So this goes way back to the very, very first week of the semester. There's some function of x times n derivatives of the unknown function y. So a naught of x times n derivatives of y plus a1 of x times n minus 1 derivatives of y plus dot 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 plus a n minus 1 of x times y prime plus a n of x times y. And then if you remember, this is all equal to some capital F of x here on the right-hand side. I don't know if you remember this or not, but if you glance back into your notes, way back to January, you're going to see this equation in your notes there. Okay? Well, what I'm going to do now is I'm going to rewrite this equation using the D notation. So everywhere that I'm taking a derivative here, I'm just going to put in a D to represent that derivative. So for example, right here, so I'm going to rewrite this. By the way, I'm also going to stop writing the x in here. I'm just going to write a naught. Okay, but it's really a naught of x. All right. And then this is n derivatives of y. Well, n derivatives is going to be d to the n, right? And this is of y. I'm going to put the y way over here, though, so that I can put some more terms in the middle. So this is a naught n derivatives of y. And then plus a1 times n minus 1 derivatives of y, plus dot dot dot, plus a n minus 1 times 1 derivative of y, and then plus a n. And all of that is equal to capital F. Okay. So I've just abbreviated things a little bit, but this is the way it would look. So if you literally imagine distributing this sum out to the y's, you're just going to get each one of these terms that's sitting right here. Okay? This is just a combination of linear operations. So this whole thing is linear again, and in fact, to make things even more abbreviated, I'm going to take that whole parenthesized expression now and call it L. L. L is going to represent that whole thing on the left side. So my new differential equation, after I incorporate L, is really, really, really small. L of y equals f. That's my new form. Okay? So we can write our differential equation in a very compact way using these d's and then ultimately the L notation. Let me just show you a quick example of how this might be applied on a problem here. Similar to a homework problem or something like that. So let's imagine, let's let L be equal to the following expression: x minus x squared d squared plus sine of x times d plus 2x plus e to the x. Okay? So let's take that to be L. Okay? And let's take a function, an input to this. This is like a linear transformation, right? This This is a linear operator. I'm going to take it and apply it to an input. Let's apply it to e to the 3x plus 2x. We can just make something up here. We'll apply it to that. So what is L of y? I just want to practice this. So let's compute L of y. Come back over here again. Remember, you can rewind anything that I'm erasing too quickly here. Review it again. So L of y, let's see what that would be. Okay. Well, that's going to be x minus x squared times 2 derivatives of y. That would be y double prime. Plus the sine of x times 1 derivative of y. And then plus 2x plus e to the x. People sometimes forget that that also has to be multiplied by just y itself, right? The y, right? You're putting L of y, so it's of y. There's a y over here. Each of the terms is being applied to y. So this is what you would have. Okay? So let's see. We have x minus x squared times, we need to take 2 derivatives of y over here, right? Let me just take my derivatives right now. The first derivative would be 3 e to the 3x plus 2. And the second derivative would be 9 e to the 3x. Okay? So the second derivative, I can put that in here. It would be 9 e to the 3x. Okay? Then the next term, we have a sine of x and a y prime. Y prime is 3 e to the 3x plus 2. And then finally, plus 2x plus e to the x times y itself, which was e to the 3x plus 2x. So this would be the answer. Okay? This particular exercise is really just practicing the notation. Okay, there's nothing earth-shattering about what we've done here. I just gave you a linear operator. I plugged a function into it, which involved taking a couple of derivatives. Notice that the order of the differential equation here, the highest number of derivatives that we see is 2 derivatives, which corresponds to having d squared right here. Okay, so that kind of makes sense. Now, let's bring in some more of the linear algebra into this discussion. So you remember that anytime you have a linear transformation, such as L, any L here is going to be a linear transformation. That linear transformation always has a kernel. We've talked about the kernel of a linear transformation. So we can talk about the kernel of any linear transformation L. Okay? And what would that be? Well, the kernel of a linear transformation L, this would be the set of inputs. Those would be the functions that you're plugging into the operator. They're the functions that get killed by L, right? That get transformed to 0 when you apply this operation to them. So this is the formula for the kernel of L. Okay? The kernel of L. Now, the kernel, you guys will remember that the kernel of a linear transformation is always a subspace, right? It's a subspace. So, essentially, what you can do then is try and find a basis for that subspace. So here's a quick theorem, all right? The set of solutions to L of y equals 0, okay, in other words, the kernel of L, this set of solutions forms a vector space. There's the linear algebra coming back again. It's a vector space, okay? It's a subspace of the space of functions, n times differentiable functions. And it's a vector space of dimension n. Now the n that we're talking about is just the, so let me just remind you, the n really comes from the highest power of d that you see in the expression for L here. So if this is what L is equal to, then the most number of derivatives you're going to see is n derivatives, right? Like this example, L had a d squared in it, and we see that the highest derivative that we have to look at is the second derivative. So the n is the maximum number of derivatives. Well, the kernel of L is a vector space of dimension n. I don't have to really justify that it's a vector space, because anytime you take the kernel of any linear transformation, you get a vector space. Right? That was back in the chapter 6. Right? The kernel of any transformation is always a subspace of V when t goes from V to W. So the kernel is always closed under addition and scalar multiplication. So it forms a vector space. And the dimension is n. N is the dimension of this vector space. Okay? So I just want to show you like the weight of that, like the importance of it. This is extremely cool, what I've just shown you here. Because let me give you a problem. Let me give you a problem. I'm going to show you why this is an awesome theorem. Okay, this is really an awesome theorem. Here's an example. I'm not going to make it a hard example. It's going to be a really, really simple example. Let's solve d squared plus 1 of y equals 0. Okay? D squared plus 1 of y equals 0. Of course, remember, that's really just d squared just means two derivatives of y, and then plus 1 times y equals 0. This is just rewriting the differential equation in a slightly different way. Okay? Well, what we're really solving for here is, okay, so here's the thing. Here's the thing. What we're really being asked for is, so we need to find the kernel of the operation, this is my L, by the way, my operation d squared plus 1. We're looking for the kernel of that. Which functions get killed by that? Right? Which functions, when you take two derivatives of them and add them to themselves, cancel out to 0? This is what we're being asked to find right now. Okay? So, if you need to pause the video, this would be a good time to pause it, and during the pause, I want you to think if you know any solutions to this. Do you know any functions such that after you take two derivatives of it, it essentially becomes the negative of what you started with? So you're thinking about functions, you differentiate them twice, they become the negative of what you started with. I'm going to give you a moment. You can pause me if you want to, and think about that, because this is something you should be able to think about from calculus, some functions you might know. Think about functions that would satisfy this equation. Go ahead and pause me if you need to, and then I'll talk to you about the answer, okay? Okay. Hopefully you had enough time to think about this. So if you are on top of your calculus and you remember how the derivatives of those basic functions in calculus work, you've probably thought of these two functions. Sine of x. If you take two derivatives of sine of x and add it to sine of x, you're going to get 0. And another example of a function that would solve the same equation would be cosine of x. Okay? Now, these two functions are not scalar multiples of each other, so I want to make the note here that those two functions, y1 and y2, that set of functions is Li. We have two linearly independent solutions. We are talking about an L that has a two-dimensional kernel, right? The dimension of this set of solutions is 2. The dimension should be 2. We have two, so we have the right number of functions here, which is 2. They are Li. So here's the punchline. If they are Li, and it's the right number of vectors, then they also must span the space. So y1, y2 spans the kernel of L. Oh, and that is the big, exciting punchline. Because the thing is, all right, so you might have thought, this wasn't so hard to find these two solutions, But how do you know there isn't some other solution out there? How do you know that we can't use a natural logarithm or an exponential function in some crazy combination, maybe with some quotients or products or chain rules or whatever, some crazy function y that after you miraculously take two derivatives of it and add it to whatever it was you dreamed up, you cancel it out to zero? How do you know you can't do that? This is how come you know that you can't do that, right? Because the kernel of L, the solutions to this equation, they are already fully spanned by just these two solutions, right? Every other solution, every other function that is in the kernel of L that solves this equation, every other function is a linear combination of these two, and that is so exciting. That means we don't have to keep looking. We don't have to keep wondering if we found all of the solutions to this equation. The answer is yes, we did. The set of all of the solutions to this equation are just linear combinations of these two. So sine of x, cosine of x, 3 sine of x minus 7 cosine x, right? Any linear combination of these two solutions will give us another solution. However, those are all of the solutions. There's nothing missing. There are no other solutions out there that we would have to look for. That, to me, is really awesome. That is really awesome. Okay. I hope that makes sense. I always get excited when I go over that. I hope I'm as excited on the video as I am in person when I'm talking about this idea with this example specifically. Because, yeah, you could sit here and say, I could spend all day just thinking of different functions that might solve this equation. Who knows? Maybe there's some weird thing out there that would work. No, nothing weird can work. It's got to be linear combinations of these two. You have a basis here. This is a basis. That means that everything in that vector space, everything in the kernel, everything that, in other words, solves this equation is just built from these two solutions right here. There's no other mystery about it. Okay. I might just take a quick minute and address one final point here, which is, in the case of a two-dimensional space, and we have just the two solutions here, it was pretty easy to just look at it and say, yeah, I know that these are Li, because they're not multiples of each other. But a question that you might have in a more complicated problem or a higher order differential equation might be something like this. Given n solutions, let's call them y1, y2, dot, 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 yn. Suppose I have n solutions of a differential equation. So if I have a differential equation and I find n solutions, how can we tell if that set of solutions, y1, y2, dot, 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 up to yn, how can we tell if that set is Li? That would be maybe not an obvious thing to answer. Here it's easy, because these two functions are not scalar multiples of each other. But in general, it might be a little bit trickier to figure that out. So what I want to do is I'm just going to take a moment and tell you how to do this. I don't know that I'm going to fully justify it right now on the video, but I at least want you to have the answer to this question. Okay? I mean, we have the whole definition of linear independence, C1 V1 plus C2 V2 plus C3 V3, etc. If that cancels out to 0, then you want to see if the constants, C1, C2, C3, and so on, if those have to be 0. That was our classic abstract definition of linear independence back in chapter 4. It turns out that when your vectors, consist of functions, when the vectors that you're looking at are actually functions, there is another way that's a little more user-friendly, a little less abstract, that we can use to answer this question. And those of you who've been reading the book will recognize this because this was actually brought up a little bit earlier in the book than what I'm bringing it up. But the answer is something called the Wronskian. The Wronskian, okay? It's named after this crazy mathematician. The guy didn't have a whole lot of friends. He was pretty nutsy. But he did get credit for this little technique. Let me explain what the Wronskian is. Basically what you do, I'm just going to use W for it. So W of y1, y2 up to yn. Okay, what the Wronskian is, guys, what the Wronskian is it is the determinant of a matrix. And it's a square matrix. Okay? And what you do, it has to be a square matrix to take the determinant of it. What you do is you put your functions right here on the first row. Okay, so there's going to be n columns and n rows. What you do is you take derivatives as you go down the matrix. Okay, so the second row would be y1 prime, y2 prime, y3 prime, all the way up to yn prime. So you just take these derivatives and you just keep going like that. Keep going like that. The last row, how do you know when to stop? Well, you stop once it becomes a square matrix. Okay, you take enough derivatives so that it becomes a square matrix, and that's going to be n minus 1 derivatives. So y1, n minus 1 derivatives of that, n minus 1 derivatives of y2, and n minus 1 derivatives of yn. This is a square matrix, and you just take this determinant. Okay? So let me just do a quick example. If I wanted to know the Wronskian of sine of x and cosine of x, this is a pretty small example, we would just take the determinant of the matrix. So we just put the two functions right on the top, sine of x and cosine of x, and we simply differentiate down the matrix. So cosine of x goes here, negative sine of x goes here. Okay? And you take this determinant, you use AD minus BC if you want. You're going to get negative of sine squared of x plus cosine squared of x if you work that out. And that's just negative 1. Okay. Now the Wronskian is not always a whole number. The Wronskian can be itself a function of x as well. In this case it comes out to a constant, but it doesn't have to. But what the theorem is about this Wronskian, this is a tool for testing linear independence of a set of functions. And here's what the tool says. What it says is, if there is a value, let's say x naught, such that, if there is a value x naught, such that when you plug x naught into the Wronskian, so you take your n functions, you calculate the Wronskian, and then you plug in x naught. Now here, if you know, it doesn't matter what number you plug in, you always get negative 1 as an output. Okay, but like I said, sometimes these Wronskians will come out with x's in them. If you can plug in a specific x into that Wronskian and get a non-zero result, okay, so this it would be a case here, in this example, well then, if that is possible, if that happens, then your functions, guys, then your set of functions is, in fact, Li. Then your functions form a linearly independent set. So this is a test for linear independence in the case when you are talking about functions. Okay? This is an easy way around. You cannot use this Wronskian for vectors in Rn. You can't use it for matrices, right? You can only use it for functions. So you could use it for polynomials because a polynomial is a function. Okay? So, you know, if I wanted to, this is one more quick example here. I mean, I could do the Wronskian of x squared with x cubed. Okay? Test these guys to see if they're linearly independent or not. So this would be x squared and x cubed, and then this would be 2x, and this would be 3x squared. Take the derivatives, and now you have a square matrix. And when you use the AD minus BC method here, 3x to the fourth minus 2x to the fourth, Well, that would just be x to the fourth, right? So here's an example where the Wronskian has x's in it. And